Hi, Pre-Calculus Honors. So these are Note 6.1, Day 2, Applications of Vectors. Go ahead and read through the objectives for today's lesson. Okay, so the velocity of a moving object is a vector because velocity has both magnitude and direction. The magnitude of velocity is speed. So let's consider this plane flying on a bearing of 300 degrees. Recall that a bearing of 300 degrees, that's measured from north clockwise. So if this is a 300-degree angle, our angle in standard position, there you go, would be 150. So we talked about how to write to describe an angle, the vector v in component form. So we could say 450 cosine 150 and 450 sine 150. And remember we talked about how I like to use the angle in standard position. If you wanted to use 30 degrees and describe A and B, right? And again, the magnitude of v is the velocity. You could have said cosine 30 is A over 450 and said 450 cos 30, but remember that it's in quadrant 2, so again you would have to put a negative sign there. And the sine of 30 and the sine of 150 are both positive. So there you go. You also could have described 450 sine 30. But again, I like to use this because, again, I might forget to put my negative sign. Okay, so let's think about this. So if you type this into your calculator, you get negative 389.71, comma 225. So let's think about what we did. We just described the velocity vector by its horizontal and vertical components. You also could have said v equals negative 389.71i plus 225j, because again, that's like when we write that it's like a linear combination, and I is the horizontal and j is the vertical component. Okay, just to make sure you understand what we have here, it's the components of the velocity give the horizontal, westward, and vertical, northward speeds. So, to sum it all up, the plane travels 389.71 miles per hour westward and 225 miles per hour northward as it travels 450 miles per hour on a bearing of 300. So again, if we kind of think about a vector as the hypotenuse of a right triangle and we break it down into its x and y components. Okay, let's talk about the next example. Go ahead and read number 2. Okay, so let's draw a picture. So the plane is flying on a bearing of 170 degrees at 430 miles per hour, and the wind is blowing with a bearing of 200 degrees at 70 miles per hour. So again, we need an angle in standard position, because again, when I grab my calculator assumes that the angle is in standard position. So I end up with 280 for the plane and 250 for the wind. Now when I go ahead and write this in component form, again, I'm describing the horizontal and vertical components of the velocity of the plane and the horizontal and vertical components of the velocity of the wind. So what we're going to do now is combine forces. So what is actually happening? Again, the poor pilot, the pilot is trying to fly the plane in this direction, but again, the wind is going to have an effect. So let's see what's actually happening when you combine the plane with the wind. So we can add the x's and the y's together. Go ahead and grab your calculator. Make sure you are in degree mode. All right, so we added the x's and the y's, and so here's what's actually happening. Okay, so the magnitude of the velocity vector is the speed of the plane. So you could find the magnitudes. You could say 50.73. And again, notice that the point as at the origin is really the distance formula, because we have a point out here at 50.73 comma negative 489.25, but the origin, so you're really just subtracting 0. So you don't even have to write it in there. I'm not going to even write it in there. So we're going to go ahead and square. And then again, the distance will technically, because negative 489.25 is the y minus 0 is the origin. So we have the initial point. It's in component form. And we take the square root. So the magnitude is 491.87 miles per hour. So that's how fast the plane is really flying. Now, as far as the direction goes, we need this angle right here. So you can use trigonometry Again, make sure you're in degree mode. And that's a 3. Good job. Okay, so inverse tangent, and we end up with an angle of negative 84.08. The problem is they want a bearing. So think of this angle as like a reference angle, and if you want a bearing, it's from north clockwise. So for the bearing, you would have to say 90 plus 84.08 degrees. So you end up with 174.08 degrees. Okay, so for our last plane example, I think this one's a little tricky because they're not really telling you the bearing of the plane at the beginning here. They're just saying, oh, the plane can fly at a speed of 450 miles per hour if there's no wind, but it's not even telling you, what's going on here. But they did tell you that the wind is blowing at 65 miles per hour at a bearing of 60 degrees. So again, we're going to use the angle 30 in standard position. I think I'm going to erase that so that I don't accidentally use the wrong angle. And then notice they also told us what actually happened. That the plane, it says, what is the bearing the pilot should follow for the plane to head due east? So the plane, we want the plane to head due east. So again, we don't know what the actual speed is, but we do know that the sine of 0 degrees is 0. So that's going to help us later, that the y coordinate of what actually happened is 0. So let's think about this. Go ahead and if we call, again, let's try and guess what's happening. So notice if this is what actually happened and the wind is pulling it this way, notice that the plane has to be, so the plane, would actually have to be in quadrant 4, because notice the wind is pulling it this way, so it's going to end up going east. So that's how we know that it's somewhere over here. We know that, again, they told us 450 miles per hour, but we don't know this angle theta. Okay, so go ahead and write in component form, plane with wind. The velocity vector, plane with wind. We need the horizontal and vertical components. Go ahead and pause the video and give it a try. We're combining forces, the velocities here. We added the plane with the wind, the x's with the x's, the y's with the y's. So now what I want you to do is think about this fact that our actual, this y component was 0. So we know that of 450 sine theta plus 65 sine 30 must be equal to 0. So we could actually solve this. So if you take negative 65 divided by sine 30 divided by 450, take the inverse sine, you should end up with negative 4.14, which makes sense because, again, we guessed that this angle was in quadrant 4. So now you could go back and find the actual speed. All right, so notice we want this is what actually happened, right? And so what we want to do is we want to find the magnitude of that velocity vector. So this is our x component, this is our y component, right, or our horizontal and our vertical. So when we find the magnitude, we get 505.12 miles per hour. We also need the bearing. So the bearing of, actually, I don't know if they asked us that, but, oh, yes, actually they did. Here it is. What is the bearing the pilot should follow? So notice this bearing is 90 degrees plus that reference angle of 4.14. So bearing of 94.14. So that's the bearing that the pilot is attempting to fly. Again, the wind is making the plane actually go east, and this is the actual speed. Okay, next we're going to talk about inclined planes, and I will tell you that sometimes I think students get confused by inclined planes, but here are a couple things I want you to remember. I want you to remember that when we think about a vector, we're going to break it down into its components. Okay, so you might want to think about a vector as a hypotenuse of a right triangle, and think about its horizontal and vertical components. Now, what's confusing is when we have an incline, is we're thinking of x's and y's, horizontal and vertical, but now it's on an incline. Okay, so that's why it's a little bit confusing. So let's first of all just think about what types of questions they might ask us. The force of gravity. So again, the force of gravity, wouldn't that be the weight of the box, W? And again, gravity is pulling that box down towards the center of the earth, right? So AC is a component of that weight. I'll change that to a different color. Okay, and again, when you get to physics, we'll have all sorts of things like friction and normal curve and things like that. But here in math, like I said, we're going to just kind of really just simplify things and think about right triangles. And again, think of a vector as the hypotenuse of a right triangle. So we've got a component of gravity that tends to hold the box against the surface of the ramp, and then we have another component of gravity that tends to push the box down the ramp. Okay, and so again, notice that AD and CB are equal, right? AC, DB. So what I would like you to do is think about these two examples here that I gave you some triangles, and we're going to talk about how you could figure out, for example, that this angle right here of the incline was 20, and how did I know that this angle, this cute little angle right here is 20? So that's what we're going to talk about next. So go ahead and pause the video and think about that for a minute. Okay, so I just summarized what I said up here, that AB is the weight of the box. There's a component of AB that is perpendicular to the incline, namely AC, and a component of AB that is parallel to the incline, namely AD. Okay, so again, we are going to think about vectors. Let me just repeat this again. We're going to think about vectors as the hypotenuse of a right triangle, and that's how we're going to figure out angles. Okay, so looking at this example, so again, we have a cart racing down a ramp. Notice this is angle theta. And again, you wonder, oh, how does this person know, hey, this is angle theta over here? But if you think about it, here's our right triangle. This angle has to be the complement, since this is a right angle right here, 90 minus theta, right? And aren't these lines parallel, right? Because again, the weight of the cart, that goes down to the earth. And so that's how I knew that this angle right here was also 90 minus theta, and that's how I knew that this angle was theta. So let's look at another example. Let's look at this one. So again, in the right triangle, this angle was theta. This is a 90-degree angle, so this angle is 90 minus whatever theta must be. These lines are parallel, right? So think about your same side interior. If you have two, parallel lines cut by a transversal, but again, from geometry, we should remember, or actually just look at the picture. If this is a right triangle, if this is theta, that's 90 minus theta, right? And that's how I know that this angle right here is theta. Okay, I'm going to show you something with GeoGebra. Okay, so for GeoGebra, I think this just goes way past what we're going to talk about, because again, we're not going to talk about normal or friction or things like that. But I just want you to focus on angles right now. Okay, so if we're just focusing on angles, and again, remember we're thinking about a vector as the hypotenuse of a right triangle. So, for example, if I have this angle theta, remember we talked about how we know this is parallel, right? So this must be the complement, 90 minus theta, and so then we know that we've got that angle right there. Let's see here. Got it. So again, I thought the picture was slightly confusing because let's see, it's not going to work. So notice this is a right angle here, and so that's how we know that this angle right here is the same as this angle right here. Okay. So we can make some changes here. We could change the angle. Oh, I better erase that first. Erase, 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 erase. Okay, so again, you can kind of watch that. And again, I think it makes it a little bit more obvious that those are the same angle. Okay, so back to this example then. Here we go. So it says a force of 30 pounds just keeps the box from sliding down the ramp inclined at 20 degrees. Find the weight of the box. So again, this is our vector. We're breaking it down into its components, right? And again, AD, CB equal, right? AC, DB equal. So go ahead and, again, think about how this angle is 20. So if they tell us that a force of 30 pounds just keeps the box from sliding down the ramp, okay, so that would be 30 pounds right here. That would be parallel to the ramp. So that's the component of gravity, AB, right, of the weight of the box, that just keeps the box from sliding down the ramp. So that would have to be parallel to the incline. So now you could say the sine of 20 is 30 over the weight of the box. Because again, in this is a right triangle right here. Sine of 20 is opposite right hypotenuse. Okay, so you could find 87.71 pounds. Okay, let's practice a little bit more on finding angles. So for number 5, go ahead and pause the video. I need you to find theta for A and B. Pause the video and give it a try. All right, so for part A, I've noticed that this angle right here is 35 degrees. So again, these lines are parallel, so I know that this 55 and 35 must be complementary. And over here, again, I know that this angle right here and 50 must be complementary. So if this is 50, this is 40, and that's how I knew that this angle right here is 50, because again, we have a right triangle. Okay, let's do another example. Number 46, go ahead and pause the video and read and try and do part A. Okay, so notice there's a force of 2.5 pounds, and it's parallel to the incline. So we want to break that down into its horizontal and vertical components. But again, when you're on an incline, I think it's confusing to say horizontal and vertical components. So just think of 2.5 as the vector we are referring to right now, and we want to make that the hypotenuse of a right triangle. So notice we put it in component form, and again, when they want component form, they want it with respect, notice, to the horizontal. Okay, so we could go ahead and do that. Now, let's just see if you really understand what we did. If I found the magnitude of this vector right now, let's think about that. If we found the magnitude, do you know what the answer would be? Hopefully you do. If you type this into your calculator, you get 2.5 pounds. Well, of course it's 2.5 pounds, right? Because we know that that's the magnitude of the force, that vector. Okay. Go ahead and think about part B. Pause the video and give it a try. Okay, so the 2.5 pound force is parallel to the incline, and again, the horizontal component of that force is moving the box forward. The vertical component is the force moving the box upward against the pull of gravity. Go ahead and read number 6, okay, and then pause the video. I drew a picture for you. Again, I was able to find that this angle was 10. Think about how I did that. These lines are parallel, and this angle over here would have to be 80, right? So I knew that this was 10 degrees. So go ahead and pause the video. We want to find the magnitude of the force. Then again, when I say the force, it's the weight of the car. 1,800 pounds is W. That's the magnitude of W. To keep the car from rolling down the hill would be A, and then B would be that force, the component of that force that is perpendicular to the street. Go ahead and pause the video and give it a try. Okay, so there you go. The force of gravity has a component. Force of gravity, W, has a component perpendicular to the incline that holds the car against the surface, and a component parallel to the incline that keeps the car from rolling down the hill. Okay, one last incline example. A 50-pound force that makes an angle of 25 degrees, yes, there we go, so this is 50 pounds of force right here, is pulling a box up the plane. The inclined plane makes an angle of 18 degrees with the horizontal. So go ahead and pause the video and try part A. Remember, they told us a 50-pound force, so again, that's our vector, and we're going to think of every vector as the hypotenuse of a right triangle. So we're going to break it down into its components, but again, it's confusing because, again, we're talking about, you don't want to say x and y because notice we're on an incline. So we have parallel to the incline and perpendicular to the incline. So we want A right there, we want this particular component of the 50-pound force that's parallel to the incline. So you could say cosine of 25 degrees is A over 50, and you find A is 45.32. And that makes sense that A should be less than 50 because, again, 50 is the hypotenuse. That 50 pounds must be bigger than the 45.32 pounds. Okay, let's think about part B now. When they say the component form, that would mean with respect to the horizon, the horizontal. So for part B now, we have to consider, again, our 50-pound force, but we have to consider the horizon. So we need this angle right here. And isn't it true that if this is 18 degrees, that this angle right here must be 18? Maybe I need a bigger picture. So here's your incline. Here's your box, right? This angle, here's our 50-pound force. This angle was 25. So again, Make this another color. Maybe make it more obvious that there's your horizon. And that's why I know that this is 18 degrees. So now when we're talking about our right triangle here, you would say 50 cos 43 degrees and 50 sine 43 degrees, because 18 plus 25 is 43. So this is how you would describe that 50-pound force in component form, because again it would have to be with the horizon. This angle is 43, or sorry, with the horizontal. This angle is 43 degrees. Now again, if you find the magnitude of this, and I know you probably think this is a waste of time, but I just want to make sure you understand this. If you find the magnitude, go ahead and type this into your calculator. You should get 50 pounds, because again, 50 pounds, that is the magnitude of this vector, right, of this force. Okay, last example, go ahead and read about the pep rally. All right, so let's think about what we did. So we've got the math teachers. This is a 28-pound force, and I gave you the direction of this vector. We have a 25-pound force, right? So notice if we describe the math teachers and the science teachers separately, now think about it. If we want to combine forces, you would add the x components and the y components. I typed this into my calculator, and this is what's actually happening. So let's think about what's actually happening. So the teachers, we have something like this going on. $51.16, and okay, I actually did a bad job. Looks a little bit more like that. Again, it did kind of a bad job, because that's negative 1.90. Okay, so these are the teachers. So the students would be equal and opposite, since they're at a standstill. So here are the students. So that would be negative 51.16 and positive 1.90. Okay, so the last thing we need to do is find the magnitude. So go ahead and give it a try. Okay, so finding the magnitude of that vector, you'd realize that the students are pulling at 51.20 pounds of force. Great job, everyone.